So some real-life applications of impulse momentum, the impulse momentum theorem, is as follows. In vehicle safety, we can look at some examples, and in sports, we can look at some examples. So in vehicle safety, we know that all cars these days are fit with seat belts, crumple zones, and airbags, right? And this is all just to make your journey safer in case of a collision, because a net force will be applied to your body to change your momentum from a high value eventually to zero for you to stop. And if that time interval of the collision can be extended, can be made a bit longer, if that can be increased, that collision time, then the output force will be less on the driver. And we say that things like airbags and crumple zones in a car and wearing a safety belt softens the force acting on you. So an arrestor bed for trucks is simply one with a lot of gravel. And what would be the function of that gravel? Obviously, to perform a frictional force, to exert a frictional force on that truck in case the truck's brakes fail and they lose control of that truck. If it comes downhill, it will build up a lot of momentum and it can cause a great amount of turmoil in traffic, where that truck can then drive right over other cars and over maybe people. But they built these arrestor beds sort of as ramps on the side of the road, fill them with gravel and give it some sort of incline so that the truck can be stopped in two ways, namely friction acting on it in the opposite direction of motion to eventually act as that net force through a certain interval of time, which will change the momentum of that truck from a high value due to a lot of momentum to zero to eventually make it stop. It's also built at a bit of an incline so that the car will obviously now gain potential energy, and in that process, the gain in potential energy will be offset by a loss in kinetic energy, which is exactly what that truck needs to stop. All right. And eventually for the driver and everyone else to be safe. We said that cars are fitted with seat belts. That is to increase the contact time or the collision time for you as a driver not to hit the steering wheel instantaneously when you collide with something in front of you in a collision, so that the force, that net force then acting on you from the steering wheel will be softened. We say the net force will decrease. An airbag does exactly the same. It deploys when you get into a collision, and what it does, in fact, it gives you some distance that that airbag will act against your body to increase that collision time before you actually hit the steering wheel, which will soften the force on you. Rear and front crumple zones. A car is built these days to crumple. It must crumple. Back in the day, they made Chevys and very fantastic cars that were so hard, if you just knock the wall of your house, you will just go right through the house. The car will not have a dent, would not have had a dent on it, hardly anything, because it was made so strong without crumple zones. But that would mean that that force, that net force acting in that collision on those old cars would all be transmitted immediately to the driver. And there's nothing to increase the collision time in the form of compartments in the front and rear to actually crumple and increase that collision time. So all of that net force would have increased, that's transmitted to you as a driver, but it just works the other way these days, which is brilliant. So in sport, impulse momentum that theorem is basically applied in follow-throughs in any sort of ball sports and catching a cricket ball. So as you've seen with the baseball being hit, there is quite a follow-through from all the way from the back on that bat, so that you get quite a large net force acting for a longer time, contact time on that ball, in order to make it fly and in order to change its momentum from some negative value to some positive value. Remember, it's changing direction, or even from zero, just before it starts moving again, coming through a negative velocity, zero, and then positive to a much higher momentum. And as we know, momentum, that change of momentum, that impulse will impart on the ball, will then immediately transmit in the form of a change in velocity. And that is what you want, the greatest change of velocity due to that greater change in momentum, and the greater impulse on that ball due to a follow-through in sports. Catching a cricket ball, you would have seen that if anyone does field work and catch a cricket ball, they always move their hands with the direction of that hard ball, so that they increase the contact time, that time interval through which the force, net force, acts, which will then change the momentum of that ball from some high value to zero. But if they increase that contact time, it actually softens the force. We say it softens the net force acting on their hands, and it will protect their hands, so that in case of that collision, if you stop a hard ball abruptly with your hands, it can actually break the carpal bones in your hands. So you need to actually know how to catch any sort of hard ball like a cricket ball. Now, this is just quickly two scenarios of where the time duration over which a net force acts can change the outcome drastically. All right. So here's a crash test dummy, and there's no crumple zones or anything in that car, and it hits a wall, and immediately that net force is transmitted through acting on the person or that dummy in the car, and that can create quite a lot of damage and can actually be fatal. So a rapid change in momentum can create a huge net force. Where does that net force go? It goes to the driver of that car, and you get whiplash, and you can hit the steering wheel with a very great force, which can eventually be fatal. So the opposite to this is if an airbag deploys, as we've seen. This is the airbag, right? The minute you have a collision, that airbag opens up, and you will move forward, hitting that airbag. And now, before you just make bare contact with the steering wheel, that airbag will increase the contact time, or will increase the collision time to change your momentum. Your momentum will change. Momentum will stay the same whether you have no airbag or you have an airbag fitted in your steering wheel. But that just a little bit longer time for that force to act over will now decrease that net force drastically, and that can save lives. So we say, according to the impulse momentum formula, impulse, as we know, is F net delta T, which is equal to M delta V, or the change in momentum. If you just extend that collision time with some factor, you make that collision time maybe 5-10 times longer than what it would be without an airbag, as we've seen up here. That for a given change in momentum, which is constant. Remember, this impulse will stay the same. It will stay constant because it's still you in that car, whether you have an airbag or no airbag. Your mass in motion will go from some high value, to zero eventually. So that change in velocity times mass will stay constant. But if you extend the contact time to then offset that change, the net average force has to decrease, or it will decrease. So that output force on you will be much less than if there was no airbag fitted. Let's go back to this example, and we see that in fact you have the same formula, but for the same constant change in momentum of that body, if you decrease the contact time, because you decrease the collision time, there's nothing to actually soften the blow, then that net average force output will be so much greater. And that, of course, can be absolutely fatal. So always wear your seatbelts. Make sure that your car has airbags in it. And of course, hopefully, some crumple zones.